one and all present here. I am Sumi Yadav and I feel privileged to welcome you all at Ahmedabad University Research Seminar Series. The goal of this seminar series program is to enhance intellectual environment of the university and to facilitate student research progress. Research is what we are doing, and at that time we don't know what we are doing. So we feel honored to have with us our today's speaker, Professor Brian Cantor, Vice Chancellor of the University of Bradford, UK. May I now request Professor Rishi Shankar, Associate Dean, School of Arts and Sciences, Ahmedabad University, to kindly occupy the chair on the dais. Thank you, sir. I now request Professor Pankaj Chandra, Chairman, Board of Management, Ahmedabad University, to occupy the chair on the dais. Thank you, sir. May I now request Guest of Honor, Diana Anderson, Established Chair, Biomedical Sciences, University of Bradford, UK, to kindly occupy the chair on the dais. Thank you, ma'am. I now request our honorable speaker, Professor Brian Cantor, Vice Chancellor, University of Bradford, UK, to kindly occupy the chair on the dais. Thank you, sir. I now request Professor Pankaj Chandra to welcome our guest by presenting a memento.
To Professor Cantor that Ahmedabad is very well known for its old city, and that heritage city has areas where people live with old architecture, both of homes and otherwise, which are called poles. This is a replica of one of them. I hope it will help you remember Ahmedabad when you come back.
Thank you, sir. I now invite Professor Rishi Shankar, Associate Dean, School of Arts and Sciences, Ahmedabad University, to introduce today's speaker, Professor Brian Cantor, to our esteemed audience.
Good morning, everyone. Professor Cantor, Professor Chandra, Professor Diana Anderson, distinguished colleagues in the audience, and my dear students. It is indeed a pleasure and privilege for me today to stand here before you and introduce you a person of an order you will see as he speaks later, which is very hard to find in the world today. And in Professor Cantor, we have not only a Vice Chancellor at the University of Bradford, United Kingdom, but he is also an acknowledged authority, world authority on material manufacturing. An area which is developing, because this is the one area where with nanotechnology we are now going into molecular manufacturing. So it is indeed a privilege to have him with us today. The University of Bradford, under his tutelage in recent past, has made major strides in higher education league and is one of the handful of major climbers by 10 places in the last year of 127 UK institutions. This tells itself it is ability is to make an institution of academic learning go up the steps faster and recognition of that order. The university ranks in top 10 in the 5 subjects, and one or two of them are of major interest to us, and that is in physiotherapy, forensic sciences, ophthalmics, occupational therapy, and medical technology. And we have in this institution at AU, engineering and biology. And this is where we want to go in terms of affordable healthcare, biology, and engineering. So we are definitely in league in having him here with us. And of course, this university also ranks, the University of Bradford ranks 118th in the world universities, and in the top 100 in the universities which came up in the world in the last 50 years. He has, in his earlier moving in the career, has made a park which is called the Beckbrook Science Park at the University of Oxford, and was the first academic director of this park. He masterminded the installation of a 7.8 million pound atomic engineering analysis equipment as early as 1999, and which opened the park's business incubator, arrival of a company called Ox, the first spin-out, and the Advanced Materials Center at the University of Oxford. This was the beginning of the university's business model in Oxford, and therefore he is one of the pioneers in terms of Oxford University's entry into this area. He has served on the boards of York Science Park, to name a few, Kobe Institute, Yorkshire Innovation, National Science Engineering Learning Center, the Center for Low Carbon Futures, and the worldwide universities networks he is very much into even today and moving it faster. He has served as advisor for organizations like NASA, European Union, and government and non-government agencies across the globe. Based on these and other learnings and his service to society, the Queen in England recognized him with CEB, Commander of the Most Excellent Order of the British Empire, as it is called, for services to higher education in 2013. He invented the field of high tropy alloys when we come to research, and his research has investigated the manufacture of materials and has contributed to fundamental scientific advances as well as improvements in many industrial products which we are using today. He has published over 300 papers with 7,000 citations and is listed in ISI as one of the most cited researchers. He was awarded the SNAM Prize, the York Lifetime Achievement Award, and the Rosenheim and Platinum Medals of Institute of Materials. Professor Brian Cantor is recognized in many places in the world, and I'll name a few. He's the honorary professor of 3 Chinese universities. He's also the Chinese Institute of Materials Research honorary professor. And of course, most of you remember at home, the Indian Institute of Science, Bangalore. He's the honorary professor at Indian Institute of Science. Honorary member of the Indian Institute of Metals, and the member of Academia Europea and the World Technology Network. He is also the fellow of the Institute of Materials, the Institute of Physics, the Chartered Management Institute, and the Royal Academy of Engineering. So these are some of his few accomplishments, and there's a long list, I cannot go on, it's several pages. But one thing I must say, that in Professor Brian Cantor, we have what is called a model academician and a researcher. And it is indeed a privilege and a pleasure for me, both personally as well on behalf of the Ahmedabad University, to welcome him to this auditorium to say a few words and enlighten us with his learning. Thank you. Yeah, we'll just, all the dignitaries on the dais, please.
Well, thank you very much, Professor Shankar, and let me thank Professor Chandra and Professor Shankar and all of you for being here. I'm so privileged and proud to be invited to your great university, a new university, but growing dramatically well. It's a great pleasure and a privilege to come here, and I'm so pleased so many of you came here to hear me talk. You know, there's a slight danger in giving the present. Slight danger in giving it before the talk. because I did consider picking this up and running it off so I didn't have to give them thought. But of course I wouldn't do that. Well, I did ask before I came if it was okay to give a technical talk, so I am going to move into the technical aspects of the talk, but I'd say a quick word or two about my career, seeing as Professor Shankar was so nice to say a few things about it. And there's many students here in the audience, so I really don't want to talk to students directly. Some of it will be a bit technical, and if it's a little bit too technical, never mind, but there'll be some lessons to learn anyway from the technical side, so stick with it. But let me just say a few words personally, as you've just heard about some of my achievements. I've had a very, very fortunate career. I was born and brought up in the middle of Manchester, which is a big industrial city in the north of England. I came from a very working class background. I was very fortunate to get to Cambridge University. That was the first piece of good fortune in my career. I've had many pieces of good fortune in my career, which I won't bore you with. Everybody gets good fortune. Everybody gets good fortune. And it's your talent and ability which allows you to make use of that good fortune. Everyone has some bad fortune too, and your talent and ability sees you through over the difficult times. My career divides into three sections. The first 10 or 15 years I was working as a pure scientist. I was excited about the way that atoms and molecules and electrons could be organized within a material. I was a kind of physicist, a bit of a chemist, but I was interested in how the atoms and molecules and electrons could be organized, the range of possibilities. And I worked on a lot of fundamental issues in that. I had the good fortune to come here and work in India for a year at Banaras Hindu University in 1980, towards the end of this period of pure science. And shortly after that, I went to work at GE, the big US multinational in the US. And I worked on two major industrial projects there, because the atomic and molecular and electronic structures I was working on had potential application. And I changed my mind. I stopped being interested in, no, I didn't stop being interested. I continued to be interested in how atoms and molecules and electrons are arranged. That was the core of my science. But I also began to be interested in how you could use that to improve people's lives through making great products, which is what GE did. I then went to the University of Oxford and continued my career. Even though I moved back into academia, I had become an applied scientist, an engineer, and interested in materials manufacture and how you actually made things out of the structures that were possible within a material. So I spent about another 10 or 15 years as an applied scientist, working with many of the big multinational companies, working with many spin-out companies, young start-up companies, developing new high-tech products of all sorts in many different sectors. Materials science, fortunately, is a very broad-based subject. I worked in the aerospace sector, in the automotive sector, in the energy sector, in the IT sector, in the home electronics sector, in the energy sector, because materials underpins everything. So I was able to work with in some great areas on some great projects which would help people's lives. And I then, for the third part of my career, moved into university management. And that's when I became, first of all, head of science and engineering at Oxford, and then Vice Chancellor of the University of York, and then Vice Chancellor of the University of Bradford. And I moved increasingly into management. And I'm quite proud of the fact that I have, as well as having some scientific and engineering qualifications, I was appointed to be a fellow of the Chartered Management Institute, because that meant that I had really done a reasonable job in management. And I have had great fun and pleasure helping organisations like the University of York and Oxford University and many other organisations in the community grow and move forward. I've had the pleasure of founding a medical school, founding a law school, founding many research institutes in neuroscience, in environmental science, in the arts and humanities as well, in theatre and film and TV studies. So I've had a very varied career, and I've been very, very fortunate. And people often say to me, this is my first bit, so there are some lessons for all of you students in what I say. The first lesson is this, for me, and I say it to all of my graduating students when they get their degrees. Because people sometimes say to me, Brian, you've done very well in your career. You're very ambitious in your career. I've never been ambitious in my career. The two guiding lights for me have been to enjoy myself, doing exciting and interesting things, and if possible, to make a difference to improve people's lives. And I think every student should find something you really want to do, which excites you, which has an impact, which is going to improve the world, and then you'll have a great career. So that's the first lesson. I just wanted to go through that because listening to the wonderful description of myself, I wasn't sure if I really recognised myself, but anyway, that's how I've run my life. I've just tried to do what I thought would be exciting and interesting at the time, and in my career it's worked out pretty well. I've done okay. I'm going to talk a little bit about this field called high entropy alloys. It's some of the work I did in my fundamental period, so it goes back a long way. It begins in the late 70s, this field, when I was interested in the structure of materials, the structure of atomic and molecular and electronic structures, and the opportunities. And I was working for a long time on all sorts of different ways you could make materials, and trying to understand how you could control the atomic and molecular structure. Maybe it works through this one. It's not moving. Okay, sorry. I think it deserves a round of applause. Okay. Okay, so as I said, I'm going to talk about, on a technical basis, about some work that I began as part of the fundamental research and ideas I was thinking about, which goes back to the late 70s. Which, as I said, my fundamental period kind of finished with the year spent in India, in Benares, for a year working at BHU. And then it launched into my more commercial research, which began when I went then to GE in the States. Anyway, I was working on all sorts of different kinds of materials and trying to understand and control the electronic and molecular and atomic structure. And I began to think about how we made the materials that we do make, and what the range of materials we have available are. And I called the problem the issue of multi-component alloys, or if you like, we're going to use the word alloys to mean materials here. An alloy is a mixture of different elements. It's usually used in metallurgical science, a mixture of different metals. But a material is a mixture of different components, different elements, or different compounds. So for what I say from now on, alloy will mean material, and component will mean element or compound. So we make our materials by mixing up different components, different elements, different compounds to make each material, to make each alloy. And I began to think about the problem of what I call multi-component alloys, when we use many different compounds or elements to mix up to make a material. So I called it multi-component alloys at that time. Many years later, in the last 5 or 6 years, it began to be called high entropy alloys. So that's why the talk is called multi-component and high entropy alloys. But I probably won't say very much about the entropy aspect of the alloys. I may mention it. But what I was really thinking about was, why are the materials that we have the materials that we have? I began to think about what I call the alloying strategy, the materials strategy. How do we decide the composition of the materials we have? So this is a very simple level. I wasn't really asking about the atomic and molecular structure and the electronic structure. That's what I was working on with many materials. But I began to think to myself, we've been very, very conservative in the actual compositions of the materials and the alloys that we make. We've been very conservative. So I want to explain, and this chart shows, let me see if this works now, I'm a bit nervous about it. No, I think this is better. So, I shall say a few words about the multi-component alloying strategies and underlying principles. I shall then talk a little bit about this particular set of materials, which you can see is quite a complicated, very multi-component system. It consists of all these elements mixed up. And it's this type of material, which was the first material which we made, which was a multi-component material in 1979, 1980 and 1981. I won't have time to talk about all these other examples down here, but there's a lot of other different examples which exemplify many of the things that I will say. So the idea I had was that there is something called conventional alloying strategy, what I now call conventional alloying strategy. This is the way we normally make our materials. And actually, we've made them this way for the last several thousand years, since human beings began to make materials. Probably in the Stone Age, we probably just found them and shaped them a little bit, but then in the Bronze Age, we began to mix different elements to make bronze, as the Bronze Age implies, and then later we moved into making other things. In the Iron Age, we began to make steels, and then now in the modern world, we make many, many different kinds of materials, which are out of which we manufacture all of our world, whether it's polymeric materials, or whether it's ceramic materials, or whether it's semiconducting materials, or superconducting materials, or whether it's in biological materials which we manufacture now. So we make materials, and for most of in fact for all of the last several thousand years we've been doing it, we've used one general strategy. We may not have recognized it as a strategy, but we have used one strategy. What is the strategy? The strategy, as it says at the top there, is we take one major component for the main property we want. So if we want to have a thermally resistant material, we will normally pick a ceramic. Bricks are thermally resistant, concrete is thermally resistant, they're ceramic materials. We build our houses out of them to keep the heat in if you're in the UK, or the heat out if you're here in India. They're thermally resistant, they don't let the heat transmit through them. But you know, they're basically made out of calcium carbonate. If we want a high conducting material, so we can have high electrical conducting, we start with copper, because it's one of the highest conducting materials we know, and it's very convenient to make copper. If we want to have a very malleable material, we usually use a steel. We base it on iron, which is a very malleable material, can be drawn out to make car bodies and tin cans and things like that. If we want a high temperature material, we might choose, if we want it to be metallic, nickel, because nickel has very good high temperature properties. If we want a ceramic or something like that, if we want a transparent material, we start with silicon dioxide, silica, because it can be quite easily cooled to be made transparent. If we want a semiconductor, we start with silicon, because it shows semiconducting properties. We choose the basic material because of the main property we want. And then we add a little bit of a number of other things to give it secondary properties and to slightly beef up the primary properties. So if you take copper for an electrical conductor, it's pretty soft copper, pure copper, even though pure copper has the best electrical conductivity. So you add a little bit of beryllium. Actually, beryllium is not a very easy element to use, but you do add. Most high-strength copper conductors are made out of copper beryllium. Or if we want to be able to manufacture it in certain ways, we add a little bit of tin to make a bronze. It's easier to cast and therefore to make it that way rather than make it by other methods. If we want to make our window glass, we don't make it entirely out of silicon dioxide, because it's actually, silicon dioxide doesn't form a transparent material quite as easily as we like, so we add a little bit of sodium dioxide, Na2O, to make it slightly easier to cool and make it a glass, i.e. an amorphous atomic structure, a molecular structure, and therefore it's transparent, so that's easier to manufacture. So we add secondary components to make the secondary properties, but we add rather small amounts because we want the primary property. And sometimes we do that, if you take a nickel superalloy, which is what our aero engines are made out of, high temperature materials, they've been developed tremendously well. You know, when the first turbo engine was developed by Frank Whittle before the Second World War, it was thrown out. The person who was looking at it said, this will never work, it'll never fly, we don't have a material with enough high temperature capability. The only reason it was successful after the war, jet engines, was because they discovered nickel superalloys. Nickel superalloys are basically nickel for the high temperature property, high temperature strength, but then to make it stronger you add a bit of aluminium and a bit of titanium, a small amount of aluminium, a small amount of titanium. To make it corrosion resistant you add a bit of chromium. And actually a nickel superalloy now has maybe 4, 5, 6 additional components. You add a tiny pinch of boron to prevent the crystal size within the material changing, to keep it the right size. So there's a whole series of little, but they're all in little pinches. The primary stuff is nickel still. Now the materials I was working on, we were trying to make new electronic and molecular structures. And in a sense, we were doing what I call extended conventional alloying strategy. We were beginning to make more interesting and unusual properties and get unusual properties with unusual structures of materials, unusual atomic and molecular and electronic structures. And the way we were doing it was, we weren't going by the rules. The rules were, there weren't really rules, but this is just what people, this is the received wisdom that people had, is that you start with a primary property and you add a little bit of this. And if you add too much, it won't work, because it becomes impossible to make. That was the basic received wisdom. Nobody wrote it down as a rule, but everybody knew that. That's what you did. And in order to make unusual structures, we were going beyond the rules. And it's what I call extended conventional alloying strategy. Yeah. And we found some interesting things. So to give an example, the Nobel Prize was given about 3 years ago or 4 years ago to Danny Sheckman, who's a good friend of mine, who discovered quasi crystals. Quasi crystals are materials with five-fold symmetry, which had been said for many, many years by crystallographers were impossible. They weren't impossible. When Danny Sheckman brought the picture that he had from his diffraction machine, the electron diffraction pattern, to John Kahn, his supervisor at the National Bureau of Standards where he was working, and said, I've got a five-fold symmetric diffraction pattern, John Kahn said, go back and redo the experiment, it can't be right. Redo the experiment, it was right. They discovered five-fold symmetric structures, which had been said were impossible. When Paul Dewey, about 10 or 20 years earlier, who didn't get the Nobel Prize, but he would have done if he hadn't died before he would have got it, they said you can't have an amorphous metal. Not possible, they said. And he added a material, a mixture of palladium and phosphorus, and he discovered it was amorphous, and it could be made amorphous. And then there's now literally thousands of metallic glasses and amorphous metals. There's literally thousands of quasi crystals being found. The same thing was true about high temperature superconductors. They reached the maximum with nickel titanium, and then suddenly, in a lab in Geneva, they discovered much higher temperature superconductors. And they won the Nobel Prize. So people began to find these unusual structures with unusual and valuable properties. But what they were doing was they were going beyond the normal rules of alloying. And in the late 70s I began to think about this, and it occurred to me, and this is the basic idea, that actually we hadn't really tried with our materials. Although we've been working for thousands of years on different materials, and although research in the most recent decade or two has been very intensive, we really haven't tried very hard. So I said, what we've never done is mix up several components, several elements, or several compounds in near equal proportions. Nobody's ever done it. Nobody's ever done it. It occurred to me. I didn't know of a material where you took, say, 3, or certainly not 4. Occasionally there were ternary systems, 3-component systems, with 3 materials, 3 components added, in near equal proportions. Usually That was very, very rare, actually. Occasionally there were 2 components in near equal proportions, very rarely 3, and never 4 or 5. I'd never heard of such a thing. I'd never heard of many components being added in equal proportions, or near equal proportions. We had multi-component systems like the nickel superatoms I mentioned, or like stainless steels, where you had a primary element, and then you'd added maybe 5, 6, 7, 8 other things, but only in little pinches. So everything we knew about was either a single component, a couple of components added in fairly equal proportions, in substantial proportions, or a single component with a lot of pinches of stuff. But the idea of having 3 or 4 or 5 or 6 or 7 or more components in near equal proportions, never done. I've never seen anything, and I still haven't seen that ever done before 1980, when I asked a young man who was working with me as an undergraduate student. So you can do great work as an undergraduate student. He was an undergraduate student, Alan Vincent. He worked with me, did a 100-hour project, and I said, I've had this rather crazy idea. Why don't you try making a material which contains a lot of different elements or components or compounds in equal proportions? Let's see what we get. It was a very simple idea. By the way, I talked to a lot of people about it, and they all said, "You're crazy. Why would you do that?" I said, "I don't know, but it's not been done before, and it sounds sort of interesting. Maybe something will happen." Anyway, it's now a very big field. It's called, I call it the multi-element alloying strategy, where you add a large number of components in equal or near equal proportions. In the last 5 years, I think Professor Shankar said, I'm on the ISI list of most cited material scientists. It means I've written a lot of papers, a lot of research, some fundamental, some applied, and people have quoted my papers as they've made progress, and most science works that way. I was put on that list in 2000, around about 2000, 2002. I stopped doing real research in 2002. We published, for complicated reasons, we didn't publish this work, which I'm going to show you in a minute, which we did in 1980. We published it in 2004. It's almost the last paper I've ever published. That is now my most cited paper. Because in the last 5 or 6 years, it's become an enormous field, literally hundreds of people working on it. And they have discovered, through this process, many, many new kinds of materials with many exciting properties. And there are many more to go. Can I persuade you of that? I hope so. What I'm really saying is this. Think of a ternary material made of 3 components. The way you represent the 3-component material is on a triangle. And the apexes of the triangle are the 3 components, A, B, and C. And anywhere in the middle of the triangle represents a composition somewhere between A, B, and C. And what I'm saying is we know a lot about the individual components, the individual elements, the individual compounds, and we occasionally add a little bit of B into A. So we know in this region here, or C into A. Sometimes we add B and C. So we know the regions near the apexes of the triangle, but we don't know much about the middle, which is where you get the 3 components mixed equally. It's very rare in a ternary system, in a 3-component system, that we have made materials in the middle. It's even rarer if you have a quaternary system, which is a tetrahedron, with a 4-component system. It's even rarer to have made that. In fact, I don't believe it had ever been done before the late 70s and early 80s when we did it. And if you go to a 5 or 6 or 7 or 8 component system, I can't draw the figure, but there is the equivalent thing in higher dimensions. A 5-component system, all the possible materials in that 5-component system can be represented in it's a virtual way of thinking about it, a 5-apex hedron, polyhedron, or a 6-apex polyhedron, or a 7-apex polyhedron, and in the middle, no one's ever looked. So we can ask ourselves the question, very simply, how many materials could we possibly make? And how many have we actually looked at? So that's the question I asked myself. We did the experiments first. I'll show you the experiments in a minute, and what we found, and what is exciting people right now. But the question we asked ourselves subsequently was, well, how many materials could we make? And the answer is shown here. I don't want to bore you too much with the maths. It's a very simple bit of maths. If you have C components, 3, 4, 5, 6, I just showed you ternary and quaternary 3 or 4, C components, then you have to say to yourself, how much can I change the composition to move from one material to another? Now, anyone who works with different materials knows that you specify materials typically to 0.1 or 0.01 or 0.001%. Actually, very often you need to specify them more accurately. If you're in a semiconductor material, an extra part per billion can change the semiconducting properties. If you're in a steel, there are certain components, if you change it by a part per million, you change the properties very substantially. So some of the specifications are much tighter than that. But let's be fairly conservative, and let's say if we change the system, the composition of the material by 0.1% of any of the components, then we've got a different material. 0.1% normally we specify more accurately than that, because it changes the properties, it changes the material sufficiently that it matters. But let's be reasonably conservative and say changing the composition by 0.1% changes the material. That means for each component, there's 1,000 different steps from 0 to 100%. So the problem of how many materials we can make out of our C components is the same thing as saying, if I take 1,000 atoms or molecules, and I can draw those atoms or molecules from C different types of atom or molecule, how many ways can I do it? That is the same thing as saying, how many materials could I have? Take 1,000 atoms, because if I change any of those atoms, I'm changing the composition by 0.1%. That's why it's 1,000 atoms. That's why it's, if it differs by 0.1%, 100 over 0.1 is 1,000. So that's the number of atoms you need. So it's the same thing as saying, if I've got n atoms, and I've got C components which I can take each atom from, how many different ways can I do it? And the answer is this. It's a fairly simple bit of combinatorial analysis. That's the number. It's factorial C plus n minus 1 divided by factorial C minus 1 divided by factorial n. Don't worry about it, it's a formula. I got it wrong when I published it. There's a little gap here. That's what I used to say, and when I'm talking to more technically minded people, I tell them that was wrong, so they have to ignore the wrong answer, because I did it wrong. It is actually, though, a very simple bit of combinatorial maths. That is the true answer for how many ways you can get a material, if different materials can count as differing by the composition in 0.1%, when you've got C components. And how many components could we use to make our materials? Well, let's take the elements for simplicity. That's our palette. We can choose any of the elements. You probably know there's about 110 different elements, but quite a lot of them are toxic, quite a lot of them are radioactive, quite a lot of them don't last very long, quite a lot of them are unusable. There's about 60 components you can use, the things I've talked about: nickel, sodium, chlorine, iron. There's about 60 total out of the 110. So if we've got 60 components, we can imagine that all the possible materials are contained in a 60 apex polyhedron, and the composition is somewhere in the middle of that polyhedron. And the number of points which are separated from each other within that polyhedron by 0.1% is given by this formula here. And if we put in n as being 1,000, i.e. x is 0.1%, and we put in the C as 60, the answer is the number of different materials you can have is 10 to the 100, which is a big number. You probably know 10 to the 100 is called a Google. And the reason Google, not this Google, the more famous Google, is called Google, is because there's a lot of ways you can do things, and you chose that name, but they spelt it differently. I don't know if you got the spelling wrong, or they did it intentionally to be able to patent it. But anyway, Google is Google, because the 10 to the 100 is a Google. And 10 to the 100 is a massive, massive, massive number. An unimaginable number. I haven't updated this. It's been updated recently. The number of atoms not in the galaxy, the number of atoms in the universe is estimated as 10 to the 80. So the number of possible materials we could make is 10 to the 20 times more. That's a million times 100. 100 million more materials than there are atoms in the universe. It's a fantastic number. How many have we looked at? Well, very conservatively, we might say we've looked at all the one-component systems, all the compounds and elements. We haven't looked at them all, but we've looked at a lot of them, most of them. We've looked at most of the two-component systems, the binaries. We've looked at most of those. And I've already told you we haven't actually looked at all the ternaries. And we've looked at one or two, quaternaries and quinaries, but not very many. So let's just call it the sum of the unaries, the binaries, the ternaries. That's a big overestimate of the number of materials we've really looked at. And the total number of that is 10 to the 11. So we've actually looked at, let's round it up, let's call it 10 to the 12. Let's be very non-conservative in this case. We know no more than 10 to the 12 a million materials. We don't know very much about most of those. We've hardly looked at them. We probably don't know very much at all about most of them. But let's be liberal and say we know and understand. It's a bit of an overstatement. A million materials. But there's 10 to the 100. There's a massive number of materials that have never been looked at. That's why, when people started looking a bit more adventurously, they discovered amazing things like quasi crystals, like amorphous materials, like high temperature superconductors, like superplastic materials. There's a list as long as your arm of different materials which have been discovered by fringing into this massive area in the middle of what's called phase space. There is a 60-component, 60-apex polyhedron, the centre of which is a massive unknown. And whenever anyone's pushed into it a little bit, they've found some exciting new materials. So there must be literally gazillions of more exciting materials in the middle. So I'm going to tell you now what we did in 1980, what this young man Alan Vincent did in 1980, and I'm going to tell you where the field has got to now. But let me mention what he did first. We'll leave that. We said, well, we don't really know where to start, so we said, well, let's take all the actual materials we've got in the materials locker, the cabinet, and mix them all up and see what we get. Again, not very clever, but we didn't know really where to start, so you have to start somewhere. So we made this material up, which is still the world record for the maximum number of components in any material. It's not a very important world record, but still, it's a world record, and I don't have many, so I'm going to keep claiming it until someone makes another one up. We took 20 different components. There they all are, and we mix them up in 5% proportions. Now, actually, it's quite hard to mix some of those materials. Probably one of them, there was a bit of vaporization. I don't say that's a very accurate composition, but it's a rough composition. Roughly, that's what it was. And we looked at the material we got in the optical microscope, and that's what it looked like. And then we thought, well, it looks a bit complicated. Not very complicated, actually, given there's so many different components. But we didn't quite know what to do. So we then ran an X-ray diffraction pattern on it to see what kinds of crystal structures there were there. And we immediately were amazed to discover two things. First of all, there were no more than about 3 or 4 different crystal structures in this material. That means there are no more than 3 or 4 different phases. A phase is a region of space in which the atoms and molecules are arranged in a particular way, which you can detect by the crystal structure of that region of space. The way the atoms and molecules are arranged is the crystal structure. So there were no more than 3 or 4 phases, no more than 3 or 4 kinds of crystal within the material. Now, I didn't go through it on the previous slide, but with low component materials, 1, 2, 3, the number of phases, the number of crystal structures you find in the material is roughly equal, not always, but it's often equal to the number of components. So if you have a binary system, you very often find there are 2 different kinds of crystal in the material. Not always, sometimes there's 1, but there's very often 2. If you have a ternary system, there's very often 3. So what this sample, the first thing that we discovered with our X-ray diffraction was that the number of types of crystal does not scale with the number of components. In other words, things get simpler somehow as you increase the number of components. You don't suddenly have, although this looks pretty complicated, it's not that complicated. There's only 3 or 4 different kinds of crystal in there. Whereas we might have expected maybe 20, or at least 10. We only had 3 or 4. That's the first thing we found. The second thing we found, which was the most, even more impressive, was that this matrix, the black region here, was composed of a single, what's called face-centered cubic structure with 5 components in equal proportions. It's a material that's now called, I didn't call it this, the Cantor alloy, named after me. I'm very pleased people named it after me. And it's this alloy here. Chromium, manganese, iron, cobalt, nickel in 20% proportions each. Now, no material scientist, no physicist, no chemist, no engineer would have predicted that if you mix chromium, manganese, iron, cobalt and nickel in equal proportions, that you would get only one crystal structure. It's one crystal structure, that material. Not only that, it's one of the simplest crystal structures known, face-centered cubic. Face-centered cubic is a very well-known structure. It's the structure of gold, pure gold, structure of pure copper, structure of pure lead. But it's not. It is, of those 5 components, it is only the structure of nickel. Nickel is face-centered cubic in the pure state. Cobalt is hexagonal close packed. Iron is body-centered cubic. Manganese has a structure all of its own called alpha manganese. And chromium has a structure, again, BCC, body-centered cubic. So nobody would have predicted that you would only get one crystal structure out of that material. And nobody would have predicted, if you did, if you thought it might be one, that it would be face-centered cubic. Why would you? Not only that, if you change the composition from the pure Cantor alloy, from the pure 5-component material, by changing the proportions of these 5, it stays a single phase, a single crystal structure material, all face-centered cubic. And you can add other components into it, as we discovered with Alan Vincent and Peter Knight and Isaac Chang, who worked with me on this over the next 10 or so years. Now, we didn't publish this work until, although the work was done in 1981, and Alan Vincent wrote up his thesis, his dissertation for his undergraduate degree, and he got his degree. He was a really nice young man, and he did a great job, except he didn't do a really great job. He was not a great experimental scientist. He didn't go off to become an experimental scientist. He went off to do something completely different. And the work he did was not good enough to be published, so we didn't publish it. Because the pictures were rather poor quality pictures, a bit like that one, and those ones. Those are the original ones he picked. Those are the original pictures he took, and they're rather dim and rather badly taken. They're in Polaroids. They were very rapidly went grey, and they were completely impossible to publish in a proper journal. It had been kicked out. They said, not good enough, do it again. So I asked other people to do it again, because I knew it needed to be done better. And everyone said to me, it's a crazy idea, Brian, why should we be interested? And I kept saying, but it's interesting. And they said, no, it's a crazy idea. So I couldn't get anybody to give me any money to do the work. I couldn't get anybody to do the work either, even if I had any funds. Until 1997-8, when Peter Knight, who was another young student, undergraduate, agreed to do another undergraduate project, another 100-hour project on the same thing. He repeated the work, you can see. He looked at many of the same kinds of materials and he got the same results. Unfortunately, Peter Knight was also a very nice young man, but also a pretty terrible experimental scientist. And the results were still unpublishable. So I was getting a bit desperate. I mean, I hadn't been thinking about this all the time, I have to say, but from time to time I came back and tried to do things. Anyway, in the end I said to my good friend Isaac Chang, who was a good scientist, who had been working with me did his PhD with me earlier, and then was working with me as a postdoctoral fellow, researcher. I said, for heaven's sake, Isaac, you can do a great job. If you do this bit of work, we can publish it, and then it's published. So he repeated it, and he did some beautiful research, and we published it. We went and presented at a conference in 2002, and we published it in the literature in 2004. So here's an idea I had in about 1978. The first work was done in 1981. It was redone in 1998. It was published in 2004. By that time, I was in the third phase of my career. This started in the first phase of my career. I'd gone completely through working on applied materials in the aerospace and automotive business, and I was now a university administrator. 2002, I went to be Vice Chancellor of the University of York. I stopped doing research, but at least we published the paper. And nothing happened. No one took any notice. I was going to retire from the University of York 3 years ago and go back to being an emeritus professor, and I said to myself, I'm going to do some more work on that. I think it's a really exciting idea. I said it about 6 years ago when I was planning to retire. In the end, I didn't retire. I took another job as Vice Chancellor of the University of Bradford. As you know, I was introduced that way. In the meantime, what happened? A very nice man, who I know very well, called Jin Wei Ye, who is a Chinese man, Taiwanese man, had the same idea as me in the 90s, in the late 90s, did some work in it in the early 2000s, published in the 2000s, and unlike me, didn't become a university administrator, and carried on working on it. And he called it high entropy alloys. That's why the field is known as high entropy alloys. Because he said if you mix up lots of components, you will get a lot of entropy in the material, because entropy, you may remember, is disorder, and the more things you mix together, the more disorder you can have. So they're high entropy alloys. Actually, they're not always high entropy alloys, because it depends how the atoms are mixed up. Although it is true that in the Cantor alloy, where they're all mixed together in a face-centered cubic structure, the entropy is reasonably high, because they are really mixed at the atomic level. But he called it high entropy alloys. And suddenly, in about 2009 or 10, people noticed what he was doing and got very excited. Why they didn't when I talked about it, I don't know. Maybe I'm not persuasive, and he is. I think the name was a better name, but maybe people were more open to looking for interesting things to do, I don't know. But for whatever reason, I suddenly started I was working away running universities, York, and doing other things, running companies and all the things you heard about. And then I started getting people writing to me saying, please will you come and talk about these multi-component alloys, these high entropy alloys, because you started this process, this whole field off. So I have just come here to India. I'm here now in Ahmedabad. Yesterday I was in, where was I yesterday? Sorry? Pune, the National Chemistry Lab, sorry. It's a bit of a whistle-stop tour. Pune, Ahmedabad, and then tomorrow we're going to Lucknow. So I love coming to India, and most of the places I've been to before, but I've actually never been to Ahmedabad, so I'm enjoying being here. But it's a bit of a whistle-stop tour, but I came to India from Taiwan, because the first big conference on high entropy alloys, multi-component high entropy alloys, was in Taiwan by this Professor Jin Wei Ye, with about 300 people there. And I went, and the American Institute of Materials is now putting on a regular series of conferences, and there's hundreds and hundreds of papers being published in this field. And Dan Miracle, who is a wonderful name, because wouldn't you like to have a name, Miracle? Anyway, Dan Miracle is a very good friend of mine who works at the US Air Force Materials Laboratory in Ohio, who was glued to the TV because, of course, Ohio was the key state in the recent presidential election. He was a bit worried about how it was going to go. We probably all were. But anyway, leave the politics aside. Dan Miracle, who's just written a big review of the whole field, says, we have now discovered 8 categories of new materials by using this method of mixing up different components, many of them in here. And we still haven't touched the surface, by the way. And it's not 8 new materials, not 8 individual new materials, 8 categories. One of them is the Cantor alloy. The Cantor alloy is a vast area of a new material. It's a bit like, it's better than finding a new element, because this face-centered cubic structure exists over an enormous region in that big polyhedron. Because you can change the composition, changing the amounts of these components. You can add other things into it, and I'll show you that in a second, just to prove how big it is. But they found 8 of these, and they still only hardly scratched the surface. They still haven't added much to that 10 to the 100 different materials. So there are 8 exciting new categories, groups of materials have already been found, and people are working now very hard. And they're probably being too conservative. They're probably concentrating too much on that one, because there's a whole bunch of other ones if people look. Let me show you some of the data rather quickly. So that's the work that Alan Vincent did. You can see it's not it's rather sort of greyish sort of pictures of what the structure of this material looked like. You may say, how is it that it's a single phase material? It looks like there's more than one component, more than one area. This is what's called a dendritic solidification pattern. If you have a single crystal structure and you solidify it, and that's how this was made, then you get the composition. It's all the same crystal structure, and this is all one crystal structure. The X-ray diffraction patterns show that, but there is variation in the composition within the crystal structure. So, and I'll show you that in the next one. So this is some of the equivalent things that Isaac Cheng did, much nicer. And this shows you the chromium. So the bright region is where there's high chromium, dark region low chromium. Iron, again, the darker region is high iron, and what are called the dendrites, the tree-like structure. The trees are rich in chromium and depleted in iron, but the interdendrite regions, which are between the tree branches, are depleted in chromium and rich in iron, and so on and so forth for the different components. That's called a dendritic solidification pattern, but it's still a single crystal structure with a variation in composition within it. And that's some more pictures of the same thing. And here's some information from several other studies showing that you can add to that 5-component system. You can add 8% of aluminium, or 1% of tin, or 16% of niobium, 16% of copper, 16% of vanadium, and it still says face-centered cubic, single phase, single crystal structure. What this means is within that big polyhedron, there's an enormous sea of face-centered cubic, single phase material, which can change its composition by a vast amount. So that's why I say it's a category of materials. And I can make the point even more. This is from another major review that came out last year from Murthy, Ye and Ranganathan. Murthy is at IIT Madras and Ranganathan is at IISc Bangalore. Ye, I've told you, is at the National Tsinghua University in Taiwan. And these are all materials that have got single-phase FCC, single-phase face-centered cubic crystal structure. All of those and all of those. That's one of these big categories of new materials, one of them. And if you want to, what people then discovered is, there's another big sea somewhere else of body-centered cubic structure, which nobody would have predicted. All those materials, sorry, no, those are also, sorry, I didn't give you enough. So the face-centered cubic ones are those, and those, and the body-centered cubic ones are those and those. And then the two-phase, face-centered cubic and body-centered cubic, a mixture, so there are now 2 crystal structures, are all those and all those. And they've found 8 different exciting areas. Some of them are compound structures, like there's a massive area of what's called a Lavis phase, which is an A2B type compound, and there are other compound structures being looked at, and there are high entropy ceramics being looked at, high entropy other kinds of materials. 8 have been found, and they're going to find a lot more. So I'm going to mention a couple of interesting properties about the Cantor alloy, just to give you whet your appetite for how, so you might say, so what? So it's interesting in terms of the atomic structure, molecular structure. Suddenly, I was working on atomic molecular structures and electronic structures. I've worked on them for 15 years, I said. And suddenly, I've discovered I haven't been trying very hard, because there's a massive array of possibilities. But that only goes so far. I am interested in making materials which are valuable. So this first material, the Cantor alloy, which was found, has amazing properties. And the reason it's got amazing properties is because if you have a lattice, this is a simple cubic lattice, it's not as complicated as a face-centered cubic, but the basic idea is shown here. If you have a square array or a simple cubic lattice, a crystal structure in 3 dimensions, and all these atoms are the same, well, it's very simple. But if all the atoms are different, this is 10 different components, this is 5 different components, you can see that the local structure varies dramatically from place to place. It doesn't do that if they're all the same. So, you know, the structure here around this atom is quite different from the structure around this atom, quite different from the structure around this atom, because you've distributed these 10 components, or 5 components, across the crystal structure. So although it's face-centered cubic, and it has a lot of the properties of a face-centered cubic structure, which I'll show you in a second, just to give you a flavour, it has some rather special additional properties. And the additional properties come from the fact that the local environment of the atoms varies dramatically. And the 2 most important properties, well, let me tell you the most important properties which all FCC materials have, including this one. They can be deformed very easily. Gold is FCC. You've all heard of gold leaf. Face-centered cubic structures can be deformed very easily. They can beat gold into gold leaf. You can do the same thing with lead, which is also face-centered cubic. The reason iron can be turned into nice car body shapes is because you heat it up, and at high temperatures it becomes face-centered cubic, and then you can draw it into those shapes. You can make tin cans out of it, and then you cool it down, and it gets its strength when you cool it down. Face-centered cubic materials are very soft, easy to deform. I told you with copper, with a copper electrical conductor, you have to add something to it to make it strong enough, otherwise it's too soft. Face-centered cubic materials are very soft, which means they can be drawn very easily. They don't fracture. When you draw them, when you beat them, they don't fracture, they don't break into 2 halves. They're very soft, they're very malleable, they're very ductile. So is the Cantor ion. However, unlike all the other face-centered cubic materials, it's also very high strength. In other words, you need a very high force to do that drawing. That is a very unusual combination. Materials which are soft and ductile don't fracture. They're very fracture resistant because of the softness. If you try and have a crack running through them, the softness of the material moves and prevents the crack from running. They're not brittle. Most high-strength materials, though, which can withstand a very high force, are brittle. Things like ceramics, things like window glass. It's very rare to find a material. It's regarded as the sort of the holy grail, to have a material that is both soft and ductile, as well as high strength. And these materials, they're face-centered cubic. Cantor alloy is face-centered cubic, simple cubic structure. So just because it's got the same basic structure, it can be soft, it's malleable, it's very ductile, it can be deformed a long way, it can change its shape a lot. But it does withstand a very high strength. It withstands a very high force, which is very unusual. And that's because of these different environments around the different atoms, which means that although the atoms can be moved around to make it ductile, it's very hard to move them around. So the softness of the structure allows the material not to fracture, makes it very fracture resistant, but the different environments mean that it will also withstand a very high force and a high strength, and that is very unusual. And these are some of the pictures showing how that's measured. You measure it by putting a force on the material, and you see how much it deforms. And it deforms this material up to 60 or 80 or even almost 100%. That means you can stretch it a large amount, a bit like you can with gold going to gold leaf. But these forces, or stresses as they're normally called, which go up to 1 gigapascal, are very high. And people have now discovered, with a little bit more engineering, you can go up to nearly 2 gigapascals. 2 gigapascals is as strong as almost any material we know. And 100% ductility is about as ductile as any material we know. And our strong materials are always not very ductile, which means they fracture very easily. And our ductile materials are never very strong, which means that they don't fracture, but you can't lose them in a high-strength environment. So to cut a long story short, this is how you detect it with the fracture toughness. I won't bore you with that. This is what's called an Ashby map. showing how that the two principal requirements for a material are its strength, which is on this axis, and its toughness. The toughness is a measure of how easy it is, how ductile it is, how easy it is to prevent fracture. And these high entropy alloys are up here. They're not quite as strong as the best ceramics, and one or two special metals, but their ductility, the combination of the strength and ductility is better than anything we know. And that's just the Cantor alloy. People haven't started trying to improve it. In fact, the conference I've just come from, this was plotted 2 years ago. The conference I've just come from, they've moved up in this direction enormously. And the Cantor alloy itself was quoted 2 years ago as being the best cryogenic material yet discovered, because it's particularly good at low temperatures. But now they've improved dramatically beyond that, and people are looking at it. So that's just one material out of a whole category of materials yet to be fully explored, these face-centered cubic single-phase materials, and that's only one category out of 8 that have been discovered. And those 8 are only 8 out of what must be literally hundreds and thousands and millions more. So I'm not going to show you any more of these pictures about some of these other multi-component systems and entropy systems. You can just see there's a lot of nice, beautiful pictures, which I'll flip through, which don't mean very much. I'm going to make, I think, 2 last comments and then some conclusions. No, I'm going to make 1 last comment and then some conclusions. So, I said that in the late 2000s, suddenly people began to ring me up and say, we're finding all these interesting things when you come and talk to us about high entropy alloys, about multi-component alloys, multi-component systems. And I said, no, I'm not doing any more research in this at the moment, but I still now do go to the conferences and to find out what's going on. And quite by chance, I was then Vice Chancellor at the University of York. The head of our chemistry department went to a lecture which he gave to some school children. And it brought home to me, wonderfully, the way that multi-component systems are fantastically interesting, and we've hardly tried. So what he used to do with school children was he would put a slide up. I should have done the whole thing, which he does. He put a slide up with a single letter on it, C, and he'd say to school children in their sort of age 14 or something, here's a chemical formula, what is the material? C. And most of them, 1 or 2 of them might know carbon. Most of them know. He put an O. So what is O? Average 14-year-old school child will know oxygen. And then he had another slide with H2O. He said, this is a more complicated one. Who knows what that is? And most of the kids will know water. CO2. Carbon dioxide. Not so many might know that. Then he put up this formula. He said, what's that? No idea. I've given the game away, of course. This is the chemical composition of your body. It's actually the same chemical composition if you took a dog or a horse. We're not that different from other living animals. I think if you go to the plant kingdom, you get a significant difference. But most animals have this as their chemical composition. And he works, his area of study is the influence of minor traces of different metals on the body. And he put this up to make a very interesting point, which I'll make for you because it is very interesting. So it's interesting, isn't it? Because we know the body's largely carbon, hydrogen, oxygen, and perhaps a bit of nitrogen, because that's what organic materials are made of, and we know that we're organic. That's what organic means. But you didn't know that we actually have all these other things, and we need all these other things. So selenium is in 0.00001% in the body. If you have 0.00002%, you die. If you have 0.00001, you die. But if you have 0.00001, you're fine. So we're all fine. Isn't that amazing? And the same is true for all these other ones. Our body is not very resilient to different amounts of chemicals, which is why we worry about the buildup of mercury in fish and things like that. Because you do need mercury. No, you don't need mercury. I think we can't stand mercury. But selenium is a problem. We are worried about zinc and copper. The body's quite good at getting rid of these different metals and some of the other components. If you let them get into your body, the body's quite good at dealing with it and not letting it get above the right amount and not removing it so it gets below the right amount. But it's not perfect. So it's quite important that we keep an eye on these things. That was his field. But for me, this was a wonderful description of how a multi-component system contains some of the most amazingly interesting materials. Because who would have predicted? Well, we predicted it because we know that we're alive. But if you didn't know that the humans were alive and that was an interesting material, you wouldn't consider that that would be the right composition to start from, would you? Because who would dream of that composition? So the secret of life makes the point for me, not only that it's important to control the trace elements in your body, which it is, but it also makes the point for me that there is an enormous number of exciting and interesting materials which we haven't even looked at. So that was the last point I wanted to make. I'm not going to go through all these conclusions. I'm going to go through, I think, I'm going to mention one of these, and no, I'm going to mention two of them, and then I'm going to mention a couple of rather philosophical points at the end. So the top two, let me just state as conclusions. I've said it several times, but I'm going to say it again. The vast majority of materials have never been made or studied. There is a massive number of materials, many of which will have incredibly exciting properties and interesting structures, which have never even been thought of, or looked at, or considered, let alone studied. And then, the number of phases, the only real conclusion, scientific conclusion I've drawn your attention to, is that the number of phases, the number of types of crystal you discover, when you start to look in multi-component systems, is surprisingly few. Nobody knows why. Nobody's come up with a good theory for it. There's some suggestions it might be partly to do with that high entropy thing, and there are one or two other things. But there are some sort of indications, but no real good things. So the number of crystals does not scale with the number of components. So those are the only two scientific principles I've come up with. Sounds right, like not very much, really. The vast majority of it has not been made or studied. The number of crystal structures you get does not scale. That doesn't mean to say that there isn't lots of interesting things to find. There are massively interesting things to find. So I'm going to finish with a couple of rather philosophical points. The first one is this. The potential range to study for materials is absolutely massive. The potential for us to find things to improve conditions for people is enormous. If we can find new materials with new properties, all of our advances are based on that. Our computers, our memory storage, our semiconductor systems, everything we do, our batteries, are all based upon new materials, our energy storage, and you name it. It's all determined by finding new materials. And you know, I actually went to a Science and Technology and Society Symposium. It's called the STS Symposium, which has been held for about 12 years in Kyoto. And they actually had a session called Are We Running Out of Materials? I said, and I gave a talk, and I said, material scientists and engineers have never failed to come up with a new material if you want to, if you need it. So if you need better energy storage, or solar conversion, or electrolyte capability, or anode materials, whatever. We're always finding new materials. The minute people start to look, they find new materials, which are good for that. And are we scraping the barrel? We're not. We haven't even started to scrape the barrel. We haven't scraped the surface. Is what we haven't done in the scraping business. We're not scraping the barrel. We haven't scraped the surface of the barrel. We haven't taken the cork out. So there's a massive amount of materials. So the philosophical point there is it's worth, it's a great field to study. It's a much richer field than astronomy, which is a very rich field because there's more materials than there are atoms in the universe. That's the philosophical point number one. The range of materials, and therefore the range of potential for humankind to improve how we do things and our wealth and health is absolutely massive. The second philosophical point is we are limited by our own conservatism. We've spent several thousand years not trying. So the corollary of that is, don't be too conservative, be ambitious, be exciting, be bold. The people who've been bold in the last 10, 20, 30, 40 years have generally, some of them, got Nobel Prizes, or at least they've certainly made a major contribution to some very important advances. So any of you who are interested in, and this is true, this goes beyond materials, in any area, we have a tremendous tendency to be conservative, be bold, be ambitious, have exciting ideas. I say it to every one of my graduating students at the University of Bradford, and I used to say it at the University of York. You only get one life. So there's no point being timid. Go and do something worth doing, for heaven's sake. Find something which is exciting, which is bold, which is... And if you don't, if you fall halfway short, you'll probably do something fantastic because you're trying to do something really great. So the second philosophical point, which is broader, first philosophical point is material science is an incredibly rich subject. Much richer than I'd realised. I wish I'd been, but the second point is be bold. I wish I'd been bolder myself in my career. I'm still a young man, I've got another 50 years to go. Anyway, perhaps I shouldn't push it, but I haven't got as long as you guys have. You should go out and be bold. You've got plenty of time to do that, and if it doesn't quite work, you can be bold again, and you'll have great success. That's the second philosophical point. And I think I will finish there. Whatever you do in your lives, make sure you have great ideas. Oh, no, sorry, there was a third one. There is a third philosophical point, of course. My story with these materials is, after having an idea, push it through, for heaven's sake. I mean, I was a bit sort of juddery, wasn't I? I did a bit in 1980. I did think about it in between, a bit in 98, and then finally published. I should have pushed it through early, and then this would have all happened earlier, and I'd been more active. So the three things are: materials is an incredibly rich subject. The materials about which we can make. Second one is, whatever you do in your life, be bold, decide on something really exciting, really worth doing. And then the third one is, for God's sake, work on it like crazy. Believe in your own ideas and push them through. Even when everyone's telling you you're crazy. Okay? Thanks a lot.
Still take 1 or 2